Behind every car body panel, every crankshaft, every fuselage skin, and every highway light pole sits a machine that pushed, pulled, rolled, spun, or forged raw metal into shape. Some crank out 18 finished panels a minute. Some bend steel plates over 3 inches thick. One press brake is 58 feet long. Watch to the end. A light pole bigger than a house bent on a machine. Try to imagine 2,750 tons of downward force landing on a flat sheet of aluminum in about 3 seconds. That's what a stamping press does. Not cutting, not melting. Pressing an entire piece of metal into the exact shape of a hardened die. 10 to 20 strokes a minute, coils up to 72 inches wide. Now more than double the force and heat the metal until it glows orange, and you're at a completely different level of manufacturing. A 6,500-ton hot forging press for automotive crankshafts. A steel billet gets heated to somewhere around 1,200 degrees Celsius until it's soft enough to move under load, but still fully solid. Then a die closes on it with enough force to redistribute the internal grain structure, not just squash the outside. That grain structure is why forged crankshafts survive inside your engine at 6,000 revolutions per minute for a decade. The metal fibers actually flow along the shape of the part instead of getting cut across the grain like a machined one would. Try running a 300 horsepower engine on a crankshaft that wasn't forged this way, and the connecting rod finds a new address inside your hood. The real question is what happens before the press ever gets to touch the metal. Here's the answer. Before any press ever touches a sheet, the sheet itself has to be born. And the process is bigger than most people would ever guess. An aluminum hot strip mill starts with heated ingots pushed through a rolling stand. A 4-high reversing stand squeezes them thinner and thinner across multiple passes. Dividing shears cut the material to length, and a finishing mill locks in final thickness before the strip winds onto a coiler with a belt wrapper. Automated coil logistics moves the finished product straight to shipping. One of the newest facilities of its kind in America went live in Mississippi in June 2025. And a coil off the mill isn't ready for anything yet. It's just a giant roll of raw material waiting to be cut down. That's where a slitting line takes over. The full-width coil gets unwound, run through a set of circular blades that slice it into narrower strips along the length, and then rewound as multiple smaller coils on the same machine. On this line, 1,650 millimeter wide steel gets cut into strips as narrow as the downstream press needs. The tolerances matter more than they look. A slitting line running out of alignment leaves burrs on the edge, and burrs jam a stamping die within a shift. 6,500 tons on one press! America's slitting and rolling capacity is stacking up fast. The Mississippi line is just one example. Anyone watching from the Midwest, or from Ontario, or from a European mill town, how does regional capacity actually stack up on the ground where you are? Every finished car body panel, every appliance shell, every stamped part starts as a strip that came off a line looking exactly like this one. And rolling isn't the only way to prepare material. Sometimes you push it through a shaped hole instead. That's extrusion. A carbon extrusion press takes a heated block of material and forces it through a die, opening under massive hydraulic pressure. Whatever cross-section the die has, the material comes out the other side wearing exactly that shape, like squeezing toothpaste. But the paste is heavy industrial material, and the tube opening determines whether the output becomes an electrode, a cathode, or an anode for downstream industries. One of these presses can push out miles of consistent cross-section per shift. Now take an extruded profile and add a twist. Literally, extrusion stretch forming grabs both ends of a straight metal profile, pulls it under tension until it passes the point where the metal would normally spring back, and then wraps it around a curved die. Because the metal is held past its elastic limit while it takes the new shape, it doesn't try to snap back. It stays curved. Better yet, the stretching actually increases the yield strength of the finished part. The piece comes out stronger than it went in and free of buckles, or the little dented areas metal fabricators call cans. Do the same trick to a flat sheet instead of a profile, and now you can make an aircraft fuselage panel. A sheet stretch press clamps two opposite edges of a large flat sheet in heavy hydraulic jaws. The sheet gets pulled taut in the plane. Then a shaped form die rises from below, forcing the tensioned sheet to conform to a compound 3D curve, the kind you'd see on the outside of a passenger jet. The tension keeps the surface smooth, without wrinkles or thickness variation, and the resulting part is dimensionally stable enough to bolt straight onto an airframe. And when you need a large aircraft skin panel with compound curves, including reverse contour bends, you need a machine that pulls in two directions at once. A transversal and longitudinal sheet stretch forming press ranges from 300 tons all the way up to 1,600 tons. Fuselage parts up to 50 feet long, formed in one setup. That's absolutely bonkers. All of that is one input shape at a time. But what if the shape needs to be continuous? Here's a machine that goes further than stretch forming ever could. A contour rolling machine doesn't work on two flat planes. It works in 3 dimensions, applying curvature to aircraft stringers and frames as they pass through the rollers. Instead of one big press stroke, the shape gets built up continuously through controlled roller pressure at multiple points along the length. Smooth, incremental, and repeatable. And now shrink that idea down and put it on a shop floor. A roll-forming machine for hat profiles, omega-shaped sections used for structural framing. Takes a flat strip of steel, feeds it through a sequence of forming rollers, and gradually bends it into the final cross-section. Profile length is basically unlimited. Feed rate up to 7 meters a minute. Nothing fancy, just steel going in flat and coming out shaped. Now push the flexibility further. One line that can produce 5 different profiles just by swapping spacers. A multi-profile trim roll former can produce ridge cap, extra wide ridge cap, rake trim, mini corner, and J-trim on the same machinery. The changeover is what actually matters here. Instead of rebuilding a new roll set for every profile, the operator changes out a stack of precision machined spacers that reposition the existing rolls into a different geometry. What used to take a full day of teardown can now happen in under an hour on the good ones. Try running a metal roofing plant without this kind of quick change capability. You'd need 5 separate roll formers taking up floor space instead of 1. Every product on this line comes out looking factory perfect because the same rolls do the actual forming work, no matter which profile is selected. Take roll forming to the top of an actual building, and here's what it looks like on a curved roof. The BMO Monroe system produces metal cladding profiles for free-form and double-curved surfaces directly at the construction site. A mobile forming unit gets brought right to the roof, uncoils raw material, and rolls out finished profile panels that follow the geometry of the roof itself. No length limit, no cutting to standard segments. The panels can be curved in the plane and locked together with hidden seams. Roll forming turned into a job site tool instead of a factory process. That's the twist. Try bending an 80mm thick plate of S355 structural steel across 2.5 meters of length. That's what this scene shows. A press brake ram descending onto a plate over 3 inches thick, folding it around a V-shaped die. The plate barely wants to move. The press wants otherwise. The press wins. Cut the thickness in half and increase the length, and the problem changes shape entirely. A 40mm thick stainless steel plate. 1.4 austenitic chromium nickel steel, 3.5 meters long, folded into a U-profile on a press brake. The tricky part is length. A 3.5 meter bend line means the ram has to apply force uniformly across the whole span, or the profile ends up crooked. Uneven force, uneven bend. Simple as that. Now let's talk about a real monster. 58 feet long, 2,200 tons of force, and it bends large format light poles like it's folding paper. A tandem press brake this size is built for one purpose: steel components too long for anything smaller. 2 press brakes work in sync as one unit, with synchronized rams keeping the bend line perfectly parallel across nearly 18 meters of length. The servo-hydraulic press with energy recovery is the biggest efficiency leap in this industry since CNC control landed. Poles that go on highway overpasses and stadium lighting towers all start bent on machines like this. Look under the hood of a modern press, and here's the part almost nobody sees. A servo-hydraulic drive doesn't just push oil. It recovers energy on the return stroke and feeds it back into the system. Up to 30% efficiency gain compared to older hydraulic presses. Less oil volume, less floor space, less wasted heat. The press pushes down, and the press pays for its own return trip. Here's what happens when stamping goes after the outside of a car. A 2,000-ton hydraulic deep drawing press takes a flat blank of automotive-grade steel and forces it into the compound shape of a hood, a roof, or an inner door panel in one stroke. A moving bolster carries the die in and out of the press for changeover. Swap the die, swap the part. One stroke, one panel. The next car body starts before this one finishes cooling. And a press this size doesn't earn its keep by running alone. Front-of-line automation handles blank destacking with magnetic fanners that separate stuck blanks, up to 18 cycles per minute, single or double blank. A scanner-based vision system checks every piece regardless of ambient lighting, then robotic transfer arms move blanks between successive press stations at 18 strokes per minute. End-of-line racking finishes the sequence. The bottleneck used to be the human operator loading and unloading blanks by hand. One tired person could slow the whole plant. Automation moved the bottleneck to the press itself, which is exactly where it belongs. Now heat the metal until it glows and everything changes. Long steel bars get cut to length, heated to forging temperature, transferred into the die, and shaped under hydraulic pressure. The still orange part then cools on a conveyor before CNC precision machining takes the raw, forged shape down to final tolerances. And here's what an industrial forge looks like when it's set up to produce large forged components at real volume. Steel billets get heated in induction furnaces to precise forging temperature, then transferred by robotic arm to closed die presses that shape the part in a controlled sequence. Each part goes through preforming, a rough shape. Then, through finishing, dies that press the metal into its final geometry with tight tolerances. Trimming removes the flash, which is the excess material squeezed out of the die parting line during forging. Heat treatment follows immediately. Quench, temper, or normalize, depending on the alloy and the application. The finished forgings can be crankshafts, connecting rods, front axle beams for heavy trucks, or agricultural equipment components. Anywhere a part needs the internal grain structure, only forging can provide. Every stage, from raw billet to finished component, gets tracked through digital process control, so a defective batch can be traced back to the exact heat and press cycle that created it. What's actually going to disappear first from automotive manufacturing? Hydraulic stamping presses, forging lines, or human operators on the plant floor? Modern forging plants keep tightening the loop between the material entering the door and the finished part leaving it. Open die forging is where the same principle scales up to industrial parts you can't buy off a shelf. Instead of squeezing a billet inside a closed shape, the operator repositions the workpiece between hits, working the metal into shape with a series of strategic blows. The upper die moves, the lower die stays still. The workpiece rotates, moves, and gets struck again, until a heavy round bar becomes a shaft, a ring blank, or a thick disc. Small presses handle a few hundred tons for compact parts, and the biggest ones go into the thousands of tons for shafts used in ship propulsion, wind turbines, and power generation. Try to imagine watching a piece of steel the size of a car being repositioned by a robotic manipulator while a press comes down on it every few seconds. That's what heavy open die forging actually looks like on shift. Take a hot forged blank, pierce a hole through the center, and roll it outward. That's ring rolling. Rolled rings can reach over 240 inches in outer diameter and 60,000 pounds in weight. Grain flow runs along the circumference, which gives rolled rings toughness that a plate-cut ring will never match. Now flip from a ring to a bowl-shaped piece and see how the same idea gets stretched further. Elliptical heads, the domed ends of pressure vessels. Start as a flat circular plate. A large hydraulic press pushes the plate down onto a curved forming die while rollers work the edges, gradually pulling the flat sheet into a three-dimensional dome without wrinkling the outer flange. Same idea, different rig. A large, bell-shaped tool descends onto the plate as flanging rollers work the circumference, forming elliptical, flat, toruspherical, and conical vessel heads on one machine. Anyone in the tank fabrication world know how many hours it actually takes to form a large elliptical head like this? And here's the cold forming version. Same domes, no heat. Cold stamping and flanging produce elliptical heads directly from the plate without a heating cycle, which saves energy but demands substantially more press capacity. The plate gets clamped, drawn into the die under high pressure, then transferred to a flanging station that curls the outer edge into a straight flange perpendicular to the dome. That flange is what welds to the cylindrical shell of the finished pressure vessel. Every parameter matters: plate thickness, variation, press stroke depth, die geometry. Get any of them wrong, and the finished head shows local thinning or micro cracks that only reveal themselves during hydrostatic testing weeks later after the whole vessel has been welded up. Tolerances are set to industry standards like GOST 6533-78 and 34347-2017. The same specifications that govern pressure vessels across oil and gas, chemical processing, and power generation infrastructure. But there's another way to make a curved metal shell that doesn't press anything at all. Instead of pressing a flat sheet down onto a die, spin it against a mandrel and let a roller do the work. A CNC metal spinning machine clamps a flat aluminum disc against a rotating mandrel. The mandrel shape is exactly the interior contour the finished part needs to have. The machine spins the disc at high revolutions per minute. A hardened roller then presses against the outside of the spinning disc and slowly moves along the mandrel profile. The metal flows plastically around the mandrel, thinning slightly and stretching to conform to the exact shape underneath. The finished part is a seamless metal liner. No welds, no joints, no leak paths. The liners get used for high-pressure gas cylinders that later get wrapped in carbon fiber for the final product: aluminum, steel, stainless, titanium. All spinnable on the same machine class with the right tooling. A flat disc turns into a pressure vessel liner in one continuous operation. Zero material added or removed. Get closer to the process, and here's what flowing metal actually looks like at ground level. A skilled operator pushes a roller against a spinning aluminum disc, walking it inward as the metal wraps around the mandrel underneath. The disc doesn't tear. It doesn't wrinkle. It stretches like something soft under the roller pressure. And here's where everything from the previous scenes has to come together at once. A hot blast stove dome. The top section of a giant industrial vessel that heats air for blast furnaces at steel mills. Custom press molds get designed to shape the metal in one heat press with minimal rework. Multiple welding methods join the massive sub-assemblies. Test assemblies happen before final production. A 1% deviation over a 10-meter object leaves several centimeters of error. Far beyond acceptable tolerance. Over 10,000 man-hours went into a recent dome for European steel mills. Every millimeter counts when the finished piece is nearly the height of a 3-story building. Take a steel coil, feed it into a spiral-forming machine at an angle, and out comes a pipe of almost any diameter you want. Spiral-submerged, arc-welded pipe manufacturing is one of the most efficient ways to produce large-diameter pipe. A steel strip gets uncoiled and fed into the forming section at a controlled angle. The strip wraps around itself in a helix as it moves forward, with the two edges meeting along the top seam. Submerged arc welding under a blanket of granular flux fuses the seam continuously from both the inside and the outside of the pipe. Wall thickness stays uniform because the same strip is used throughout. Pipe diameter is limited only by the strip width and the feed angle. A narrower strip and a shallower angle produces a larger diameter pipe than the same strip wrapped tighter. Every meter of finished pipe goes through hydrostatic testing, ultrasonic inspection of the weld seam, and dimensional checks before it ships to oil and gas pipeline projects, water transmission systems, or structural piling applications. Try running the alternative. welded plate pipe. And the throughput drops to a fraction of what a spiral line puts out per shift. And here's a completely opposite approach. No plate, no forming rollers. Ductile iron pipe gets centrifugally cast. Molten iron at 2,500 degrees Fahrenheit pours into a spinning mold as the machine tilts, and centrifugal force distributes the metal uniformly around the interior. Water cooling extracts the finished pipe. But finished pipe isn't finished pipe until every custom cut and every custom weld gets done at the end of the line. A worker in a boom lift welds along the seam of a large diameter fabricated pipe, then switches over to oxy-fuel cutting to open custom windows through the wall. The pipe sits on a rotating turntable so the whole circumference stays accessible. Cut lines are marked from the original plate, and a small track-mounted cutting machine follows guide rails to get the cut line exactly right. A magnet on the overhead crane holds the cutout piece so it doesn't fall inside the pipe. Some scrap pieces are worth more attention than the finished part. And here's the finish, closing two open ends of a large pipe with submerged arc welding. First, a root pass gets laid down using mag welding to seal the joint, so the following submerged arc weld doesn't burn through the first layer. Then, a tandem submerged arc welding rig. Two wires positioned one behind the other. Deposits weld metal layer by layer under a flux blanket. The tandem setup doubles the deposition rate compared to a single wire system. What takes under 3 minutes on video takes about 4 hours on the shop floor. The finished weld has to hold pressure for decades in the ground, so the machines and the operator both take their time. Turn the camera around, and here's the part nobody thinks about. The machines that shape metal are themselves complicated pieces of shaped metal. A 1,600-ton press bolster, the huge steel component that supports the die inside a hydraulic press, gets assembled, aligned, and inspected before it ever ships. Every pin, every bolt, every mating surface matters. Now watch what it takes to get one of these machines into position on the shop floor. A 500-ton hydraulic gantry lifts a stamping press frame off the transport, holds it in midair, and lowers it precisely onto its foundation. The gantry uses a power tower system, hydraulic cylinders that raise and lower the load in synchronized steps. Steerable die carts underneath let the press slide horizontally into final alignment. Miss the anchor bolt pattern by a couple of centimeters, and you're either drilling new holes in concrete that just cured, or shimming the whole press for weeks. Installation is its own manufacturing project. And when a press brake gets big enough to bend a highway light pole in one continuous curve, the numbers stop looking real. 16,400 millimeter bending length, 2,000-ton press capacity, 240-ton frame, a 37 by 10 meter work envelope. The CNC software analyzes sheet thickness, steel grade, bend length, and spring back for every stroke, and adjusts angle and depth automatically. Fully automated front and rear pushers position the workpiece. An integrated pole extraction system removes the finished part. Conical, polygonal, or high mast. One machine handles all three geometries with millimetric precision. This is what industrial steel looks like when the pole itself is bigger than a house. And here's what a shop actually looks like when it specializes in oversized structural steel. The biggest bending press in Europe sits inside a plant like this. 4,000 tons of force. The workforce calls it the Giant. And honestly, the name earned itself. Microbeam plasma cutters chamfer components in a single pass at swivel angles from negative to positive 45 degrees. And here's where every previous scene finally connects into one industrial reality. An aluminum plant is dozens of these machines running as one system. hot strip mills, extrusion presses, forming lines, coilers, cutting stations, cranes, and control rooms. Every finished coil, extruded profile, formed panel starts as raw material entering one door and leaves as a specified product from another. The scale is impossible to appreciate from ground level. Sheets get rolled thinner than a business card and stronger than the previous alloy generation. Presses cycle 24 hours a day. Cranes overhead never stop moving. Metal shaping isn't one machine. It's an entire ecosystem operating in continuous flow. Every scene circles back to one truth about industrial manufacturing. Behind every car body panel, every crankshaft, every pressure vessel, and every highway light pole sits a machine that pushed, pulled, rolled, spun, forged, welded, or cut raw material into shape. The shift happening now is real. Automation is replacing operators. Servo-hydraulic drives are cutting energy consumption by 30%. And more manufacturing is coming back to North America and Europe than any point since the 1990s. Whether the next decade rewards the biggest presses or the smartest ones is still open. So which piece of this ecosystem do you think matters most for the next 10 years? The machines themselves, the software controlling them, or the skilled people who still know how to run and maintain them? I'd love to hear your take. If watching heavy industry come alive is your kind of thing, tap the subscribe button. The next build coming up is even bigger. See you. Take care.